Welcome in this third lecture about rotation, and more particularly about torque and angular momentum. So far we have introduced the angular momentum, vector L, and systems. So today we are going to focus on rigid bodies, and then we discuss some examples of conservation of L for rigid bodies, and finally we will see an application, the gyroscope. So we have here a so-called rigid body. So how do we calculate the total momentum with respect to the origin, point O here? So this is L0, LO. So we use the usual way when we have a continuous object. We just slice it in many small pieces and we sum the contribution of each piece. So in this case we have one small piece here, so one, let's say, particle, and it has mass delta mi. So in fact delta m, because all the pieces will have the same mass in this case. Of course, if the density is not uniform, then you may have some difference in delta m's depending on the point. But in our case, this is a uniform solid. Therefore, the total angular momentum is the sum of the angular momentum of each particles. So the sum of the Li's. So each, so the the angular momentum of this point is by definition, so about this point O, it is Ri cross product with Pi, Pi being the linear momentum. So we define also R perpendicular I, which is the distance of this point to the axis of rotation. So here this point experiences a circular motion. We have R perpendicular, actually perpendicular, so by definition perpendicular to the axis, but also perpendicular to Pi, because the velocity is tangential compared to this circle. Therefore Li equal to Ri delta mvi. So mvi is Pi. Alright. So in fact here you have Ri perpendicular to Pi. Okay. This vector is perpendicular to this one. So now this may be complicated. So taking the sum may be complicated. So we are going to focus on the component along the axis of rotation. So one way to calculate that component is just to sum all the z components of each individual momentum. Okay, so let's write again what is Li. It is Ri cross product Pi, so it is represented in this in this drawing by this vector in red. So this here is in fact the triangle from the origin here to mi, delta mi, and to this point, and then coming back here. So it is in the x or z plane. Alright, so we do have Ri and Pi perpendicular. So in that case Pi is out of page. So this is the vector. Okay, so Li by definition is perpendicular to Ri and to Pi. Therefore it is here. So we want to sum the z components of the Li's, so we want to sum the Liz component. So we need to know this. So you see here I have put theta for this angle. So in fact, if you take this triangle, you see that theta is here, and then you have 90 degrees here. So if you take now this angle, this triangle, you have 90 degrees here, and that same angles, therefore this one is also theta. And LZ in such a case is Li sine theta. So we have to sum these. So here I've written again the same thing. So we know the amplitude of each Li. So we have here Ri delta M. So, delta M and VI. VI is delta was pi, okay, and we add sine theta. So we get this. Notice that Ri sine theta is in fact R perpendicular I. So you can see it here. We have Ri here, R perpendicular I here, and this is a 90 degree and angle theta. But so we would like to give to take away this linear variable and put an angular variable, which is more omega is much more friendly, doesn't depend on position, on the position of the particle in this solid. We have Vi equal R perpendicular I omega. So we replace Vi in this expression, and we get this. So we replaced, and we already had the R perpendicular here, so it becomes the R perpendicular squared. And I guess you recognize what this is. Yes, it is an rotational inertia. So let's take the sum. So we sum all the Li Z. We take the omega out of the sum because it does not depend on I, and we get this, and this is the rotational inertia with respect to the axis Z, to the rotational axis. So this is the result we get here. Z component equal IZ omega. So notice that L here does not depend on O. At first it was calculated as shown here as with respect to a point here on the axis, but in fact it does not depend on that point, it depends on the axis itself, and it makes sense because that rigid body rotating doesn't mind where you have decided to put your origin. Okay, even okay. So it makes sense that that angular momentum, that component, depends only on the axis and not on your origin. Okay, so this was for an completely arbitrary rigid body. So now let's look at more special example. The case of a symmetric rigid body rotating about an axis of symmetry. So the solid is symmetric and it's rotating about an axis of symmetry. Okay, this is important. So we have the same setup here, and we also would like to look at Liz or Li in this case. So because the solid here is symmetric about the axis of rotation, each point here has a symmetric point with respect to that axis. So it has a symmetric point here. So in this drawing, that point have a symmetric point at the same distance from the axis on the other way here. Okay, so we have another position vector here, and so in this case it is rotating in this kind of way. So pi1 is out of page, and here the momentum, linear momentum, is in the page. And if you take again this vector cross product with this one, you will find this one. So this is the linear the angular momentum for this particle. So we can take the couple actually and look at the total angular momentum of these two particles. When we have one, we have another one, a symmetric one. So we can sum actually the couple instead of just summing each particle. We sum by the couples, symmetric couples. So the total linear angular momentum of this couple is Li1 plus Li2, which is in fact something, a vector that is parallel to the z-axis. And it is in fact 2 times what we have calculated before, Liz, because we sum one vector plus another vector. So the important point is in this case, L is along the z-axis. So we have the same result, except that this time we can write it as a vector equation because L is along the z-axis. And omega is along the z-axis because omega represents the rotation, the angular velocity as a vector. Okay, so this is for if you have a symmetric body rotating along an axis of symmetry. And I is here is about that axis. Okay, so let's see some examples of conservation of angular momentum. We have already seen that if the external torque on a system is 0, then dl dt is 0 and L is constant as a vector. So let's look at here. So we have someone, and this character holds some heavy load in his hand, and he put this load very far away from his body, and which is also an axis of rotation. So at first this is the initial state, so it is rotating this way with these kind of dumbbells. Okay, so in a final state, this character will bring this heavy weight close to his body, which means close to the axis of rotation. Alright, so let's apply conservation of momentum. So this body is rotating, so this system, in fact the masses plus the character, they are all rotating, so there is an angular momentum. And it's the same as this one because of conservation of momentum. So conservation of momentum means we have this equation. So I is here the moment of inertia of this system. Alright, so how do we do so the question is, what is omega f? So we have to compare in fact I the moment of inertia in the initial state and in the final state. And typically by definition actually the moment of inertia is the sum of the mi or I squared. So it's very important, the position of these masses are very important, and the longer the distance from the axis of rotation, the larger the moment of inertia. And this is square, so it is increasing non-linearly. So which one is smaller? Is it I initial or I final? So these masses are very far away, so this is large. In this case, very close to the axis, so this is small. So I initial is greater than I final. And because we have this, of course, we have the final angular velocity greater than the initial. So this situation is in fact quite similar to that of skaters on ice, where you see these people rotating, and when they put their arms and legs away from their axis of rotation, they tend to go to rotate, to spin slowly, and when they bring all their arms and legs close to their body, they suddenly accelerate and have a large spinning velocity. So this is the formula summary for this lecture. So this is a reminder: the torque, angular momentum, Newton's second law, pure rotation. So what we have seen here new is that for rigid body, about the axis of rotation z, you have this expression for the angular momentum. And if in addition to that you have a symmetric body and rotation about a symmetry axis, let's say z, then this equation is also valid as a vector form. So we have studied so far in my lectures, we have seen a rotation, pure rotation, and you have seen before, you should have seen before, translation, so linear motion. In fact, any general motion can be represented as a combination of translation plus rotation. So this is very useful. It is very useful to isolate linear motion on one side and rotational motion on one side, because they are very easy to understand. But when you have general motion, you can have actually a superposition of linear motion and rotational motion. And in such a case, most of the time you will have to solve Newton's second law equations in both linear and angular forms. Okay, so let's now look at one example. It is a gyroscope. So gyroscope is a wheel, in fact. So this is a wheel. For now it's not rotating, and this wheel has a shaft here, and it is put on a stand here. So we define some axes. This is the origin, this is y, x and z. So if let's see, so this wheel experiences several forces, so there is in fact a reaction from this stand, and there is here the gravity. So let's say that the mass of the shaft is not so high, and most of the mass is in the wheel. So this force is mg here. So we can find that there is a torque on this object about point O. Right, and this torque is of course R cross product with mg, and it gives this green vector tau. So of course if you take the non-spinning gyroscope like this, it will fall on the ground because of this force. Okay, so there will be this object will in fact rotate about the origin and fall on the floor. Okay. So we have, of course, Newton's second law says that the torque is dl dt. Alright, so indeed it will rotate like this. Just on the, it will fall on the floor. So now next we are going to see what happens when this wheel is rotating at a very high speed. Okay, so let's while we are at it, let's just calculate the magnitude of that torque. So it's of course R mg, and the sine is it's 90 degrees, so the sine is 1, so it's mg r. Okay, so now we have a rapidly spinning gyroscope. So it's rotating like this. So it's rotating, therefore we have an angular momentum along this direction. It's symmetric, in fact a symmetric body. So we still have our gravity, we still have that torque. The only thing is that we have now a large large angular momentum here because of this rotation. So this angular momentum is L equal I omega. If we take the derivative of this, it is I d omega dt equal the torque due to gravity. Okay, so omega is constant, and let's say there is no friction, etc. So this means that I omega is constant as a magnitude, and L is constant. Okay. So, but there is something that is maybe not so intuitive, is that this system will not drop on the floor. Remember, if omega is 0, this thing just drops on the floor and that's it. In fact, it doesn't drop on the floor, and we notice that it is rotating. The whole system, shaft plus wheel, is in fact rotating around axis Z. How? So we are going to explain this behavior. So if it is why is it rotating? We have here a constant angular momentum, but there is a torque. Therefore, the angular momentum must change with time, but its magnitude is constant. So the only way L can change is in fact by changing its direction. All right? So indeed it will rotate. The only way L can keep the same magnitude and changing and still change with time is by changing direction, and this can be achieved by rotating around that axis. So you see L is here, but then it will be here, 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 so it's going to rotate. So if it's rotating, maybe we would like to know how fast it's rotating. It's spinning like this. So let's this is called the so-called precession rate of a gyroscope. So let's find out this. So here I show you in the XY plane we have the origin, we have the shaft, and we have here the wheel rotating, and L is along this direction at a time t. So at a time t plus delta t, L has changed, so our system has rotated by angle d phi, and L now, this vector is now L plus dl. So dl will be here, because L plus d. So the new momentum here is the original momentum plus the change. This is dl, and in fact dl can be defined from so dl dt equals the torque, so you can write dl equal torque dt. Okay, so this length is in fact this, and this is already interesting. Not yet looking at any magnitude, we can see that the change of L is in the direction of the torque. So L will in fact like chase the torque. The torque will be the direction of the change of L. Alright, so we want to find what we want to find is in fact d phi dt. It is the rate of change of this angle phi, so it's d phi dt. And okay, we see that in this if d phi is small, we can say that dl, this piece of arc, is in fact L d phi. Okay, like this. So now we want d phi dt, so we divide by dt. We get from this expression, we get this one, and we have dl dt, which is the torque. So we have torque divided by L. Torque, we have established that it was mgr, and L is still I omega, the magnitude. So this is in fact the so-called precession rate, big omega. So this is you can so if omega is very large, this will be quite small. Okay. So you have an effect of the mass and also of the rotational inertia. So this has several applications in planes, for example, because in fact it's all this is about resistance to change. L doesn't want to change, it is what it is, and at least here it doesn't want to change in magnitude, so it has to change because there is a torque. It has to change in its direction. But if there is no torque, L will want to stay the same, so this wheel will always stay in the same orientation. So this is useful in a plane, because if your plane is not horizontal and you use a wheel inside, the wheel will always stay the same, so you can calculate the angle of the plane with respect to that wheel and get your assiette in some sense. Alright. One last thing. We have this object in fact rotating about the z-axis. It is a precession. Therefore it must have a component of its angular momentum along that axis, in addition to the angular momentum that is along that axis due to the rotating wheel. In fact, so and this precession angular momentum would be equal to Iz omega, this omega. Right. But in fact turns out omega is very large, so this is L precession is very small, okay, compared to this angular momentum. Okay, so thank you for